Ni hao. Hello. This is the 17th lesson in heat transfer. In this lesson, we will be developing a qualitative picture of convection heat transfer that will form the basis of how we approach understanding empirical correlations that will allow us to calculate the convection heat transfer coefficient in a variety of flow situations. In this video, we will discuss how the convection heat transfer coefficient changes in flow over a flat plate. By the end of this lesson, you should be able to explain in your own words what a thermal boundary layer is, and how the thermal boundary layer is different than the velocity boundary layer. You should also be able to explain why Fourier's law can be applied at the surface of the plate. Finally, you should be able to sketch how the convection coefficient varies in the direction of flow over a flat plate, incorporating the ideas of boundary layer growth and the influence of the flow regime in the boundary layer on the value of the convection coefficient. On with the lesson.
This is all fluid mechanics, right? But now what we're talking about, well, what would be the impact of this, right, on heat transfer? So if we imagine that this plate surface is at some temperature Ts, and that the plate surface temperature is different than the temperature of the fluid that was approaching it, you can imagine that something similar might happen where it takes time, right, for the energy to move away from the plate surface and into the fluid flowing over it. And so we're going to end up with what's called the thermal boundary layer. So we're going to have a comparison and a contrast between what we call the hydrodynamic boundary layer or the velocity boundary layer and the thermal boundary layer. The velocity boundary layer characterizes the fluid mechanics, and the thermal boundary layer is characteristic of the heat transfer going on near the plate surface. So we also get this thermal boundary layer, and we can define the edge of this thermal boundary layer in a similar way to what we define the edge of the velocity boundary layer. Like eventually, the fluid particles are heated, for example, near the plate first, and there's a place far away from the plate where it's like the fluid particles didn't even know that they're now over something that's hot. It takes time for the energy to move from the plate back into the fluid particles. I'm loving that I'm seeing lots of you sketching things, because I do think it's really valuable to have a sketch like this, and that's why I'm just talking to give you a chance to have this type of a sketch in your notes, because we're going to keep coming back to it and talking about this sketch and what it means. So there is this region in which the temperature hasn't been affected, and the fluid particles flowing over this thing, it's like they're at the same temperature that they were when they were approaching the plate. And then there's a region where the fluid particles have been heated up, right? And we call that region the thermal boundary layer. And again, it's often defined, how we define the edge, there's lots of different ways of doing this, of defining the region of influence. But it's often that we say it's 99% of the change that could happen in the fluid temperature has happened, right? So this looks a little different than this U over U infinity, because what we're saying is the temperature can change between Ts and T infinity. Those are the bounds, right? They can't be any hotter than Ts, and they can't be any cooler than T infinity. And so we use changes relative to that total change as an indication of how much what's happened. So when Ts is equal to T, or when T is equal to Ts, this number becomes like big, right? And when it be small, big, right? And when T is equal to T infinity, right, becomes 1. So it's going to become small when it gets near the plate surface, and then it moves away towards 1. But it's just a way of defining where the edge is. And then the last kind of critical point is to say, what we're going to see is that the thermal boundary layer may not have the same thickness as the hydrodynamic boundary layer. It's possible to have a different thickness. So you can have a different region of influence for temperature than velocity. And we'll need a way to characterize that. And we'll talk about what that is. So it's possible that for fluid particles to be moving at their free stream velocity, but to have been heated up. Or it's possible to have fluid that has been slowed down by the plate, but it hasn't experienced a change in temperature compared to what it had when it was approaching the plate. Okay, so that's what's happening. So let's start to think about what this means then for the convection heat transfer coefficient. And we're going to do that by kind of just remembering that at the plate surface, right? At the plate surface, we have, of course, we have convection heat transfer away from the plate surface, but there's also kind of conduction, right, at the plate surface. And we can use this link, right, from the surface energy balance that says that these must be equal to each other, that somehow the heat transfer through this interface is one number. And we know we characterize it by the Newton's law of cooling, but at the plate surface where there is no slip, because the velocity is zero, we can also apply Fourier's law. That's the critical kind of conceptual link to have. So we're going to write down an equation that says, okay, at y equals 0, because we define y as the coordinate up away from the plate surface. At y equals 0, there is no fluid motion, and so it's true that we can apply Fourier's law, right, which tells us what the flux of energy must be. Now, the critical difference between this Fourier's law and the ones that we've been using in the past is that before we've been using the thermal conductivity of a solid, right? Because we've been basically dealing with conduction in solids. But here, we're actually thinking in the context of the fluid. So we're kind of, the picture isn't the greatest that I've drawn, but it's critical that this is of the fluid, not of the solid. Okay, we could also link it to the solid if we wanted to. We also say that from Newton's law of cooling, because we like to have this Newton's law of cooling with the convection coefficient, that the flux is equal to H, right, times whatever the surface temperature is at this location minus T infinity, right? Like that's what we've been saying all along, that we can quantify this convection heat transfer with this Newton's law of cooling statement. And if you give me the convection heat transfer coefficient and the difference in temperature between the surface and the free stream, I will tell you what the flux is. So these two things must be equal, right? So like 1 and 2 must be equal. So if I set them equal to each other, if I put, say, 1 into 2, and I solve for H, I'm going to get a kind of an equation for H, right? So that's what I'm going to do here. I'm going to say H is equal to, I've got the minus K thing, minus KF times dt dy. Now, where this is happening is important. This is the gradient at y equals 0. So that's at the plate surface, right? So this is at y equals 0. This is at the surface. It's not in the fluid, it's at the surface. That's what that means there. Divided by Ts minus T infinity. So Ts minus T infinity is just a constant, right? But if you look at this equation, it reveals a couple of important things when you compare it with the picture that we have over here. So one is that this H depends on the fluid thermal conductivity, right? So you see like the fluid thermal conductivity is sitting in here. So this is why we anticipate that fluids with a higher thermal conductivity are going to lead to bigger convection heat transfer coefficients. So liquids are going to be better than gases. Why? Because liquids have a higher thermal conductivity than gases do. Water is a better heat transfer media than air is, because water has a significantly higher thermal conductivity than air does. Okay, the other thing that we see is that the gradient at the surface shows up, right? So the gradient of temperature at the surface shows up. What does that gradient mean for us from the picture? It's whatever the slope is right here at the surface, right? So you see that the slope of that temperature curve that I've pictured there, that is, right, dt dy at y equals 0. So the steeper, right, the steeper the gradient is at the surface, the larger the value of h. So now let me ask you, and you can, I want you to type your answer in the chat, but don't press enter. How is that gradient, do you think, going to change, right? The gradient right here at the surface, if you're thinking about this region of influence, right, and of the thermal boundary layer, and you're anticipating that this thing growing, how is that going to change as you flow down the plate? So just think for 30 seconds.
Now, what I would like you to do is pause the video and write down an answer to the question.
I think it's going to decrease too, right? Because I'm kind of looking at this, the Ts minus T infinity isn't changing, right? T infinity is fixed and Ts is fixed. So it's the same rise that we have to make. If you think about this gradient, right, as a rise over a run, right? The numerator is kind of fixed from to some extent, and we're going to actually take advantage of this idea. So if we think about just a linear change, right? The rise is Ts minus T infinity. Actually might be minus that, right? And then the run is however thick the thermal boundary layer is. So if the numerator is fixed and the denominator is thickening up, it means that the gradient's going down, right? So we maybe could even anticipate that the h should decrease as we move down the plate. But what I really want at this point is just for you to recognize that h must depend on x, like it's going to change. So Chase, you recognize too, it's going to change. It's not going to stay the same, right? H must depend on x, like it depends on x. Why? Not because the thermal conductivity is changing, not because the temperature difference is changing. No, that's a fixed thing, right? The plate has some temperature, the fluid has some temperature approaching the plate. It's because the gradient must change as we move down the plate. And we can maybe even anticipate that it's going to decrease because we expect the boundary layer thickness to increase.
All of that qualitative picture in mind, we're in a position now, we can actually make a sketch of how the convection heat transfer coefficient, H, should change as we move down the plate as a function of X. And we also are in a position to predict what will happen at that transition point, X critical, when the boundary layer goes from laminar to turbulent. So I'm going to ask you to try to make this sketch, right, and then talk about it with your neighbor. But first, to help you, right, we can make a little substitution, which is good for thinking qualitatively like this. Awful for actually doing calculations, but good for thinking. So if you look back on your notes, you'll see that we have this expression for the convection heat transfer coefficient that we got by combining Fourier's law and Newton's law of cooling, recognizing that at the plate surface at y equals 0, where the no-slip condition exists, there is no fluid motion, and thus Fourier's law, which technically only applies for stagnant medium, applies. There's no fluid velocity at y equals 0, and so we get to apply Fourier's law there, which is why we have a gradient at y equals 0. and we have a K. This is Fourier's law in the numerator, right? You see it? It's just Fourier's law sitting up there. We said, let's make it equal to the convection, to Newton's law of cooling, because that's true, right? We want to say something about the convection with Newton's law of cooling. We know at the plate surface, we have Fourier's law. So we set that equality up to get to this expression for H, which kind of allowed us to say, yeah, the fluid thermal conductivity matters and the temperature gradient matters. That's the two things from the last sentence, right? So just for the purposes of making this sketch, we're going to think about this gradient at y equals 0 as being a line, right? We're just going to make it be linear, minus Ts minus T infinity over, it's like rise over run, right? dt over dy, the rise is the temperature difference from the plate surface to the free stream. The run, the dy, is dy, right? But that is, by definition, the thermal boundary layer thickness. Yeah. So basically what we're doing is we're taking, right, this temperature curve, which is in reality going to be more complicated than linear, it's not a line, okay? It's non-linear. But just for the purposes of making this sketch, we're just going to pretend that we can draw a straight line from the free stream temperature down to the surface, and that will be the gradient right here, right? We're just saying this is the gradient at that point in space, right there. Make sense? Okay, so now when you make this substitution in here, do you see that the minus, why do we have the minus? Because technically the temperature is decreasing as we move away from the plate surface, right? So it is a negative gradient. The minus is going to cancel with this minus, and the Ts minus T infinity is going to cancel with this Ts minus T infinity. Do you see that? So what we have left over then is, as a really super gross approximation for the convection heat transfer coefficient, we have the thermal, it's a ratio of the thermal conductivity to the thermal boundary layer thickness. Notice that the units work out here, right? Convection heat transfer coefficient should be in watt per square meter Kelvin. Thermal conductivity is in watt per meter Kelvin, and when you divide by the thickness of the boundary layer, which is length unit, we get watt per meter squared Kelvin like we expect. So now I want you to, with this kind of qualitative statement, right, how H should change, try to make this sketch. And recognize that the numerator is not going to change, right? The numerator is what the numerator is. If it's air, air has some thermal conductivity. If it's water, water has some thermal conductivity. The numerator is not going to change. But look at the sketch, right? And you can see that the thermal boundary layer thickness is going to change. And you can use that change to predict what is going to happen with H. So I want you to give it a shot, okay? I'm going to give you a minute or two to try on your own, and then I'll let you talk with your neighbor about what you sketched tomorrow.
Now, what I would like you to do is pause the video and write down an answer to the question.
Okay, so I saw lots of really good things happening out there, and I think that I saw everyone recognize that when you are in any particular boundary layer, because of this scaling dependence, when the boundary layer thickens, H is going to decrease, right? And the boundary layer thickens as we move down the plate, right? So it starts small, the thickness of the boundary layer starts small and increases. So initially, the denominator is small, which is going to make H big, right? Because if you divide by a small number, you get a big number. And as you move down the plate, the denominator is getting larger, which is making H decrease. So you'll have something that looks like this, right, in your laminar boundary layer. And you may not have drawn it curvy like this. You may have drawn it as a straight line. You don't have any information with which to kind of predict yet whether it's going to curve like this or be straight, but you should be able to see that it's going to go down, right? It is going to decrease. And because I, do this stuff, I know that it looks like this, right? So it does look like this in reality, but you wouldn't have known that. So if this were on the exam, for example, with no further information, all I'd be looking for is that it decreases. Also, to point out, at the leading edge of the plate, right, the boundary layer is technically, thickness is 0 there, right? So right at that leading edge of the plate has a temperature Ts and the fluid has a temperature T infinity, and we're getting heat transfer there. And it's really fast because the boundary layer is actually really, really thin. There is a limit, okay, and if you go and you model this region, it's not infinitely thin, but it is pretty dang thin. And so H kind of screams up towards a really, really big number. But the problem is it's restricted right to that leading edge, and it very quickly decreases as the boundary layer thickens up. At the transition point, the question is what happens, right? But at the transition point, we get a bump in the heat transfer. Why do we get a bump? Brad or Abby or Rachel, I know you know the answer. So why do we get a bump? Why does it increase?
Because there's better heat transfer to flow, but so
exactly. So Brad said in a turbulent boundary layer, right? We start over here as laminar. We get an increase in H when the boundary layer transitions from laminar to turbulent, because turbulent boundary layers are better for heat transfer. Why? Because there's mixing in the turbulent boundary layer, right? There's a bunch of mixing. Mixing tends to mix up the thermal energy and pull the energy away from the surface. You don't have that mixing in a laminar boundary layer. You have diffusion. Diffusion is slow relative to bulk motion in a turbulent boundary layer. So, the little gods that come in and stir the boundary layer up with their spoons, just like you stir your coffee, right, enhance the heat transfer in the turbulent boundary layer compared to the laminar one. Cade?
So is this because of like XCR, we're assuming it's just instant transition between the two?
Yeah, great question, Cade. So Cade said, is it really a discrete jump like this? No. Okay, in reality, it takes time for the boundary layer to transition. But so in reality, it would look something more like if it started to transition here, you'd see an increase up, and then you'd see a decrease down, and eventually it would collapse back on. So this is kind of like reality. But the way that we do problems is the black line, because we don't want to have to deal with the complexity of working out how long the transition region is and the nature of the transition, like how this slopes back up and slopes back down is ridiculously complicated. And quite frankly, we still don't, to this day, have a great way of quantifying that in a way that makes it possible to use for solving problems. So we basically kind of say, forget about it, right? We're just going to pretend that there is this snap, that the boundary layer goes from completely laminar, snap to completely turbulent for the purposes of doing calculations as engineers. And it's okay. It gives us pretty good approximations. So it works. But that's a great question. So yeah, so on an exam, I would accept the black or the green.